All right, yes. Good evening, let's start. Let me remind you what we have done last week, even though we moved to a different chapter now. We are going quite fast and the chapters are relatively independent. We define what is a K-coloring of a graph. It means whenever you have two adjacent vertices, you put a different color. I can represent a color just by a function from the set of vertices to the integer 1, 2, 3, 4, 5, and k is the maximal number I need for coloring this graph. So this is a K-coloring, and there is a name for this maximal number. It's called chromatic number with this letter chi of G. So it's a minimal K you need for coloring a graph. And I presented quickly two algorithms in order to get such a coloring. It's either the sequential vertex coloring or the largest degree. First, it means you start with the vertices with the largest number of edges, and then you go by decreasing order of number of edges. But nevertheless, these two algorithms are not very good. It depends on the graph, but for sure they are not optimal. And finding the minimal K is a hard problem. If I give you a complicated graph, you really need to work a lot to find the chromatic number. However, we have some inequalities. I don't recall what is a clique number, but the clique number is smaller or equal to this chromatic number, and this is easy to see. Because if you look at the definition of clique number, it's clear that it has to be, the chromatic number has to be bigger. On the other hand, we have a second inequality that this chromatic number is smaller than the maximal degree plus 1. And this plus 1, in fact, it happens, or you need it only for two types of graphs, the complete graph of n vertices or the circular graph of n vertices with n odd. So most of the time you can just have this inequality, but for two types of graphs you need plus 1. Then so this is true for any graph. They don't have to be represented in the plane. The next section was about plane graph. Plane graph is really something which is represented like this. For plane graph, I'm not allowed to have something like this. This is not a plane graph. At least this picture is not a plane graph because we have an intersection of two edges. So I gave the definition of plane graph. What is a face of such a plane graph? What means two adjacent faces? What is the size of a face? I gave this. And there is a famous equality which holds in this framework: the number of vertices minus the number of edges plus the number of faces is equal to 2 for any connected plane graph. And I told you there is a website which has 21 proof of this. I also mentioned a few inequalities. And the interest in these inequalities is that if you have a graph, for example, this is not a plane graph like this, but you can change it slightly if you do it like this. And now on the left, it is a plane graph. So the difference is, this is not a plane graph, this is one. So a graph which can be put as a plane graph is called a planar graph. So it's not yet as a plane graph, but there is an opportunity to make it a plane graph. And since we have inequalities, these inequalities have to be satisfied for any planar graph. If they are not satisfied, it cannot be transformed into a plane graph. And there are two important planar graphs, or non-planar. So these two graphs cannot be put as plane graphs, K5 and K33. Why they are important? Because there is a theorem which is called Kuratowski theorem, which says whenever you have a graph, if it contains in a certain sense, and this in a certain sense is important, but if this graph contains either a K5 or a K33, for sure they cannot be planar graphs. And I mentioned if somebody wants to study this, you can find information in the notes. And then there is this very important theorem which cannot be proved easily. It took a long time to prove it with computers, that any loopless plane graphs can be or is 4 colorable. So it means this chromatic number is at most 4, but be careful, this is true for plane graph. It's not true in general, but for plane graph, it's true. All right. Then I introduce the notion of dual graph of a graph. You replace faces by vertices, and you have edges between two vertices whenever two faces are adjacent. There is a precise definition, and it turned out that when you do this dual graph, a loop is becoming a bridge, and vice versa, a bridge is becoming a loop. And why we do it? Because we define also the notion of map. A map is a graph with no bridge. And we can also decide to color these faces with different colors. Okay. And the rule is now that two adjacent faces should not have the same color. And there is a counterpart of this theorem which said that you don't need more than 4 colors for coloring all maps. So all plane graphs with no bridges. Okay. These two theorems, if you prove one, the other one is just an easy consequence. So, but one has to be proved. I put something on the right. Please don't forget, if you need a grade or if most of you registered, I need to have some report in order to give you a grade. And the number is not fixed. It depends on the length. It depends on your academic age. It depends on many things, but for sure, 0 is not enough. Okay. If you have any question, you can contact me at any time. So today we discuss directed graphs. In what I've presented, I tried always to consider both graph without orientation and graph with orientation. So as much as possible, the definitions are valid for both. However, some notions were introduced only for undirected graphs. Today, we study directed graphs, so we put an emphasis on them. And 8.1 is about strongly connected component or components. You probably remember that the notion of connected, a graph is connected if, when you forget the orientation, you can go from one vertex to another one arbitrarily. I mean, you choose 2 vertices and you go from one to the other one. This is the notion of connected. Connected, you forget the orientation. Now, if we have orientations, since in the definition of connected, we forget it, it means it's not well adapted for directed graph. So we have a notion of strongly connected, which I recall. I already introduced it, but a graph is strongly connected, an oriented graph is strongly connected if whenever you choose 2 vertices, you can go from one to the other one, respecting the orientation on edges. So this one, I don't know if it is, no, it's probably not strongly connected because you can never come back to this one. You can leave this vertex, but you cannot come back to it. So for sure, this graph is not strongly connected. But the notion of strongly connected takes into account the orientation. So what is a strongly connected component? I need to define. A strongly connected component of a graph and I'm going to abbreviate this with SCC. I don't want to write all the time strongly connected component. So a strongly connected component, or SCC, of an oriented graph you can probably guess the definition. So strongly connected component of an oriented graph is a maximal. We will recall what means maximal is a maximal strongly connected subgraph of G, which means for any X on Y in one strongly connected component, there exists a path from X to Y and also a path from Y to X. So for example, in this picture, what would be a strongly connected component? This part would be strongly connected because you have only 3 vertices, but you can go from any of them to any of them. Oh, okay, sorry, okay. Sorry, yes. Now this one is strongly connected. And what means maximal? It means you cannot make it bigger. And indeed, I cannot go here. I cannot go here because there is no way to go in both directions. So this is a maximal or strongly connected component. Okay. It's not so difficult. The definition is not so difficult. Now, it's a remark. This is one strongly connected component. If I take a X here and a Y inside the strongly connected component, what does it mean between X and Y? It means either there is no path from X to Y, or no path from Y to X, or no path at all between these two. So if X doesn't belong to one strongly connected component, but Y belongs to the same strongly connected component, then either no path from X to Y, or no path from Y to X, or no path at all between these two. Or no path at all between X and Y. This is quite clear. Otherwise, there would be a contradiction with the definition of maximality. But it means, if I do I don't want to draw a complicated graph, but suppose there is inside a complicated graph, you can usually decompose it into strongly connected components. And okay. So in each circle, we have plenty of vertices. They are all strongly connected in this part, all strongly connected in this part, all strongly connected in this part. It's possible to have multiple edges because it can go from one vertex here to one here and from a different one to a different one. So this is a quite natural decomposition of a graph. So I'm going to give something about this. The definition. It's GB, a directed graph. And I'm going to give a name. Let's say this is S1, S2, S3 for the strongly connected component. And let S1, S2, up to a certain Sn be its SCC, is strongly connected component.
Why not? It's a 3 mark per slide.
But why? Okay, you're right. Thank you. Thank you. And I should be a little bit more precise because I'm speaking about the same strongly connected component. Okay, so we are in this setting, a graph on a collection of strongly connected component. Then what is the condensation? The condensation of G is a graph. It's a new graph. Is a new graph. A new graph with vertices S1, S2 up to Sn. So now each S, I do not consider it again as a certain amount of vertices. I just consider one of them, and vertices between Si on Sj if there exists such an edge in G. Edge in the initial graph. So what is the condensation of this one? We have only 3 points, and we have 2 arrows here. We have 2 arrows here, and 1 here. This is the condensation of G. I replace the connected component by just 1 point, and I keep these different arrows. But be careful, in this graph, it's possible that they started at different places, but now, of course, they are at the same vertex. So it's quite natural. But what we observe with this condensation, what is the property of this condensation? Yes, there is no cycle. Why? No cycle once we take the orientation into account. Why? There cannot be any cycle. Yes, if by mistake, of course, this is not correct, but if I had this in the condensation, it means that we would have one here. And in this case, these 2 strongly connected components would be together, and they would, this graph doesn't satisfy the maximality for the strongly connected component. So it means this is not possible. So let me write it, observation. The condensation leads automatically to a cyclic directed graph. Do you remember the name of such a graph? I gave quickly a name. It was called directed acyclic graph. But be careful. As an unoriented graph, of course, you have cycles, or you may have cycles, not always, but you may have. On the other hand, when you take the orientation into account, it's more or less like a tree. Any remark or heavy do you have any comment? No, it's not the same. It's not the same order. It makes a difference. No, but because I had introduced, I don't remember which chapter, but I had introduced this, and the abbreviation is DAG. So I cannot say, oh, this is a DAG. If you would see this word, you would complain. I know you would complain. So no. Okay, we know this. Now, in the notes, I wrote more about this, because what is nice is if I give you such a complicated graph, how do you find these strongly connected components? It's not completely easy. And there is an algorithm. So in the notes, I explained this algorithm. First, I wanted to present it today, but it would take too long. But if somebody wants to write a report about how to construct an algorithm for identifying these strongly connected components, it's a nice exercise. However, I can give you just one ingredient, or it's one result that I want to mention. So it's not the algorithm, but it's one information, because the algorithm is based, algorithm based on DFS trios, DFS algorithm. Deep, what was it? Depth first search. So you have to come back to chapter 3 or 4 about this algorithm. So what is inside this algorithm? Whenever you have to choose a new edge, choose E inside this font of GTI. This is something I mentioned at least 2 times. When you build a tree inside this graph, you have the graph, you build a tree, and at each step you have a different tree. Now you need to take a new edge inside this set. And the way you choose it for this algorithm is you choose the one with largest, what was called DF number at its origin, the I plus 1. Because remember, when you choose an edge, one endpoint has to be inside the graph, one has to be outside, or one has to be inside the tree, one has to be outside of the tree, and you choose the one with the biggest number at its initial part. Okay, so this is something we have seen. And when we do this, when constructing a tree with this algorithm, we get. So let me just draw something that we can get, and I give different names, and these names are important. So I do the simplest one. So let's suppose you get this tree when you go on with this algorithm. Still, it's not the full graph. You may have some additional edges. And I already mentioned these edges have a name. And I just want to introduce these names. So we have the tree, but we have additional edges that are from the initial graph. This one is called a back edge. it's quite clear why back, because you go from one vertex to an ancestor. This one is a forward edge because you go from an ancestor to a descendant. And what about this? This one is between two vertices and none of them is an ancestor of the other one. This one is not an ancestor and this one is not an ancestor of the other one. So this one is called a cross edge. Okay. However, and this is the last statement about this I want to mention, this cross edge has a special property. Why I put it, and I have to, with the arrow in this direction, and why I cannot have the arrow in the other direction. I cannot, it's with a DFS search, I cannot have an edge in the opposite direction for the cross edge. Can you see why? Think about how we built this tree. Yes, you go as far as much as possible, but it doesn't answer the problem. You have to finish one vertex before you backtrack. And indeed, if you would have an edge going in this direction, it means this one wouldn't be finished because you could continue. While you can, if you have an edge like this yellow one, you cannot continue because the origin, I mean, it's not going in the correct direction. You cannot go on in this direction. So let me state just a result about this. And I mention this because if you look at the algorithm for finding this strongly connected component, this remark plays a role. So it's a lemma. For a DFS tree, so a tree that you construct with this DFS algorithm, and for E, a cross edge, one has the DF number, discovery number of O of E. The origin of this has to be always bigger than the DF number of the target of E, which is exactly what I have represented it. Otherwise, there is a contradiction in how you build the tree. However, just it's maybe not clear. If you have an oriented graph, you cannot always construct such a tree for the entire graph. Because if you have some edges going in the wrong direction, you can simply not continue. But locally, you can do this. And sometimes you have to you start at different places so that you build this thing. But assuming that you can construct such a tree, then with this algorithm, you would have always cross edge going from one big DF number to a smaller one. So if somebody wants to look at this algorithm for the strongly connected component, I think it's interesting. As always, if you have any question, you can ask me. And the same for those online. If you want to ask questions, you just unmute yourself. Now we go to a second section about tournament. What it is, I need to give a definition. So a tournament is a simple directed graph. Simple, remember, means no loop, no multiple edge. So it's a simple directed graph whose underlying undirected graph, so if you forget the orientation, the underlying undirected graph is Kn. It's complete. It's Kn for some. Remember, Kn is a complete graph. So what is it? You can see it in a different way. You construct a tournament by starting with a Kn, and you put orientations everywhere. So you start, for example, with a K4. The K4 is like this. This is a K4. And I put an orientation everywhere. This is a tournament. Forget the orientation, it's a complete graph, but you put on your orientation everywhere. And we write, this is not so important, it's just a notation. We write x to y the same as x bigger than y. This is just a notation. If we have a row from x to y, we say that x is bigger than y in this. Okay. And of course, because you have it's simple, you cannot have in the other direction. If you have in one direction, you have in the other. And we also set the score of x is deg out of x. This is again just a definition. So it means how many times, it's not completely surprising because the deg out is related to how many times x is bigger than somebody else. So here the degree out would be 2, here it would be 1, here it would be 2, and so on. Okay, so we call this the score. Now, this is an easy observation. How many edges do we have in such a graph? I already mentioned it. You remember? Say it again. Thank you. This is a total number of edges, which means what is the total score? So if you add the different scores, it's the same. Total score is equal to this number. Have this number of edges starting at vertices. Okay. So these are just some notation. One more definition, which is the simplest tournament. A directed graph. It's even more general than for tournament. A directed graph is transitive. Do you remember this notion of transitive? We have seen it in many, it appears in many fields. What means transitive? Transitive is usually if A, let's say, is smaller or equal to B, and B is smaller or equal to C, then A is also smaller or equal to C. This is usually a notion of transitivity. Here it's the same. A directed graph is transitive if, now I use this notation for a directed edge from X to Y, if there exists X to Y, so edge from X to Y, and there exists an edge from Y to Z, then then take this edge from X to Z, which is this, I mean, it's always the same story about transitivity. So we say that a directed graph is transitive in this case. So you can wonder, oh, what does it mean for tournament? Now, if we are in this, so we are going to see, so of course you should start with a more complicated tournament, at least for 5 or 6, and check what it means for tournament to be transitive. And I'm going to state a few equivalent definitions. So it means each of them contains the same information. So it's a lemma, and if somebody wants to prove it, it's probably not difficult. For G tournament, the following are equivalent. So I state various equivalent notions. So first, J is transitive. Okay. J acyclic. You can check. It implies if you have a tournament which is transitive, you cannot have a cycle, but be careful, a cycle with orientation. Third one is G has exactly one Hamiltonian pass. Remember, a Hamiltonian pass means it goes through all vertices, And it's a pass, so you're not allowed to repeat the same edge, of course.
And a tournament is a direct, simply connected graph that is directed. We can't just direct all the edges, all the ways towards the point, and then it's no longer transitive.
Yeah, that's why this is the definition. So somebody is saying that not all graphs are transitive. I perfectly agree with you. Not all graphs are transitive. I'm just saying a tournament is transitive if and only if blah, 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 blah. I'm not saying that all tournaments are transitive. Not at all. So it's transitive if and only if it is acyclic, if and only if it has exactly one Hamiltonian pass. Number 4 is V admits a total ordering by scores. What does it mean? It means we gave a definition for the score of a vertex. You have a total ordering. So one has the biggest number, one has just below, 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 and so on. And this is number 5 is easy to check the set of degrees, R degrees. The set of R degrees is, if you do the list, you have 0, 1, 2, up to n minus 1. The equivalence between 4 and 5 is easy. I mean, you just think about it. It's the same information. And number 6 and last one, G has no cycle of length 3, which in a sense is easier to check than that it is acyclic, because you just concentrate on cycles of length 3. And if you can show that there is no one, then it means that it is transitive. Okay, so I'm not saying that all these equivalences are easy, but at least you have different properties of a transitive tournament. Why this situation is interesting, think about a game and you want to put a row from the winner to the loser and so on. So if you're in this situation, it's easy because you have a total ordering. So this is the simplest situation. This situation, so transitive tournament, it is easiest situation for a ranking or an ordering of vertices. Because you have naturally a first one, a second one, a third one, and so on. This is what is it? The transitive tournament is the easiest situation. But as one of you observed, not all tournaments are transitive. However, in fact, it's very rare. Not all tournaments are transitive. Still, if your aim is to, there is a question?
If G is a circle, for 6, can we just say there's no cycle of any length at all?
Yes. Yeah, this one implies 6, it's clear. What is less clear is why 6 implies 2.
Oh.
Yeah, if you have no cycle at all, I agree, this implication is easy. However, this one maybe is more difficult because here you deal only with cycle of length 3. Why does it imply that there is no cycle at all? Why there is no cycle of length 4? So now suppose your aim is to give a classification or a ranking. If it is transitive, okay, easy. What about the non-transitive case? And people, I was surprised to find that there are even entire books on this problem of tournaments. People have studied this situation, and I gave a reference to a book which is only about this topic. So, however, not then how to give a ranking to vertices. This is the aim, to vertices. I want to give a certain ranking depending on something, and how can I do it? So there is a lemma. Any tournament has at least one Hamiltonian pass. Okay. Good. But if you have more than one, what do you do? If you have more than one, then you face the problem that which one do you want to choose? And it changes your ranking. So at least you know that there exists one ranking. And be careful, this ranking doesn't always mean that it's by out degree. Here the out degree was specific. I just want to have a certain way to number the vertices 1, 2, 3, and so on. I want to give an ordering or ranking. So by the existence of at least one Hamiltonian pass, I can give this numbering, 1, 2, 3. But if I have more than one, how can I choose it? So there is a second lemma, which I like it, because it says that the condensation, try to remember I introduced the notion of condensation. The condensation of any tournament is a transitive tournament. What does it mean and what does it imply? Nice result. It means you have a tournament, complicated. What means condensation? You put together the strongly connected components. So you put together the guys which create a circle. You can go from from all vertices in a strongly connected component to all vertices in the same component. You create a new graph. Then this new graph is a transitive tournament, which means then you can apply this ordering. So you just put together the strongly connected component, and once they are together, you get a transitive tournament. So this isn't, I don't know if the proof is difficult or not. I didn't check, but at least it gives you one way to give a ranking with some having the same, some vertices have the same number with this. Inside a strongly connected component, you give the same number. So if I write it in words, the strongly connected component of a tournament can be fully ordered or totally ordered. Okay, I want to state one more definition and one more lemma, but as I said, there are books about this. Why I like the next lemma, because I put in the references a link to an article which have very nice pictures, and I put one of these pictures in the notes. And indeed, in this paper, you have several pictures like this, and this is very rare in mathematics. I guess this is the only example I know, with somebody putting such pictures in his paper. So definition in a tournament. What is a king? A king is a vertex. Sorry? No, you have to be more precise. It is a vertex which can reach all others. All others by at most 2 steps. So it means with 2 arrows, you can reach all the other one by at most 2 edges. Of course, they are oriented. So the king is you start from it, you can reach everybody, all the other vertices within 2 steps. And there is a theorem or lemma which says that it always exists. Any tournament possesses at least 1 king. So again, it's just a game. You want to give some ranking in such a framework. With the Hamiltonian path, you can do it. The problem is not unique. So how do you choose which? If it is not unique, how do you choose it? One statement says that if you do condensation, you can give a unique ordering. And this is slightly different. You give a definition of what is a king. And the lemma said, oh, they always exist at least 1. However, it happened that there is more than 1 king, and we know this. There are plenty of situations where we have more than 1 king. And then you have the definition of what is an emperor. So people have played with this a lot. So if somebody finds this interesting, okay, and I can give you more references. And apparently, maybe Schilling, you have seen this the notion of tournament before or never? Yes, in social sciences, apparently it's used quite often. And I will show you, or I will present a paradox. In fact, it's quite simple, but it's also interesting. It's called Condorcet paradox. So what is it? We consider n candidates, small n. And let n persons order them with the transitive graph. So suppose I have the letter AB up to small n. These are n candidates. And I ask each of you to tell me which one is number 1, number 2, number 3, number 4 in these n candidates. So somebody would say, oh, I prefer number C, then number B, then number K, and blah, 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 up to number A. This is the ordering I prefer, okay? And indeed, I write it like this, but this defines a transitive tournament because you can make your graph, your tournament with n vertices. C has a row in over everybody, then B has a row over everybody except the first one, and so on. So this picture is in fact equivalent to a transitive tournament. So let's suppose I ask each of you to do this. You are going to have, each of you is going to create such a transitive tournament, okay? And then I want to take all these tournaments into account. And I define what is called a majority digraph. So I consider a family of transitive tournaments. A family of transitive tournaments, and define a majority tournament by a certain rule. And what is this rule? You can guess majority. So you have, let me do it for just a few. A, B, and up to N. I want to draw a rows. I'm going to say that A is over B. So let's say A has a row from A to B. If when I look at these N things, I always compare A and B, and the majority has a row going from A to B. So if and define a majority tournament by X going to Y, the two vertices, if this row appears in a majority of the n transitive tournaments. You know, in all of them, I have either a row from A to B or a row from B to A. And I look which number is the biggest one, and I put one from A to B or from B to A, depending on this majority. Okay? Yes, I was expecting this. What happened is we have the equal number. then you just put one graph under the carpet and you have n-1, which is now odd. So I assume that n is odd. Capital N is odd. So you don't have any problem of equality. Okay, so you have a majority. Now, I mean, you decide what you do in case you have an equality. I decide that this cannot happen. So I take n odd and then it doesn't happen. Okay, so you create what is called this majority tournament. Be careful, it's not a transitive graph anymore. The majority tournament. It's a tournament because we always have either A from A to B or from B to A. It's a majority tournament, is not transitive in general. So what can happen and what is a paradox? We can have, because it depends, 3 vertices with, I will call them ABC, but of course they can be different from ABC, but I just choose 3 of them, ABC, so that there exists A bigger than B, so that we have a row in this direction, B bigger than C, but we can also have C bigger than A. There is no contradiction when you do this averaging process with a majority. You can have that A is bigger than B, B is bigger than C, but we can also have C bigger than A. Exactly this situation in this bigger graph. So what does it mean? And this is a paradox. So it means we have a majority prefers A on B, because we have an arrow from A to B. But you have also a majority which prefers B on C, and also a majority which prefers C on A. There is no contradiction. But it means if one among these 3 is elected, no majority will be satisfied. Because if you elect A, then a majority would prefer C on A. If you elect B, then a majority would prefer A on B. And if you elect C, okay, it's a majority which prefer B on C, which is like a paradox. But it's not a paradox. It's just that you are dealing with more than 2 candidates. This cannot happen if you have 2 candidates. But if you have more than 2 candidates, this can happen. Yes, one question.
They're playing a game between each other, and A beat B, B beat C, and C beat A.
Yeah, of course. I mean, you just do this with your friends, and you will see that this can happen, and there is no contradiction. But it means whenever you have an election with this framework, a majority, and with this situation, of course, it doesn't happen always. But if you're in this setting, there will never be a majority which is happy. No majority will ever be happy. Of course, this is social science. So it's this is real life. No, that's interesting. So a majority is never happy if either A or B or C is elected. So you have different solutions. And indeed, check in many countries, they only end up with 2 candidates. If you have 2 candidates, then at least one majority is happy. If you have only 1 candidate, then this is even simpler. Okay.
I think someone who's very experienced with that.
So you can play a lot with tournaments, and as we have just checked with Schilling, these things appear in social science. It's quite a simple framework, but you can still say a lot or play a lot with them. All right, last topic for today, which is called project scheduling. And we are still using oriented graphs. What is the idea? You have a big task to do, and some of these tasks cannot be done before others. So you have to finish something before you go to the next step. And we want to organize this in a clever way or in a more efficient way. So I give a definition: an activity on Arc network. Oh, by the way, yes, in this, I would say, last part of the course, I'm using different books, and quite often they use the word network for graph. And usually network is for oriented graph. So don't be surprised. Here you can just take it as a synonym of graph, and more precisely oriented graph. Not always, but quite often it's oriented graph. The network is the same. So it depends who is writing the books and what is the topic. So an activity on Arc network, which is also abbreviated AOA network. What is it? It's a weighted directed graph. Is let's say edge weight, which means I put a weight on edges. We know we can do it on edges or on vertices, but here we do on edges. It's an edge-weighted directed graph. We put an edge or information on each edge with this information. This is the weight associated to the edge E, a certain weight which represents duration, time length, duration of an activity represented by the edge E. I will do an example in a second. And what are vertices? Each vertex, I should write it like this, each vertex corresponds to event after the completion of all activities ending activities ending at this vertex. So what is it? Let me just draw first example. You start at vertex 1. Let's suppose you have different things to do. So you have activities A and B. Then once A is finished, you can go C, D, and E. And maybe then you need to connect these one. Let's say you have another one. Okay. This, and we have orientations. always going in a certain direction. And on each, so each edge, as I said, is an activity. You have to do something. And you put a number, a weight. Let's say this one takes 2 hours. This one is 1 hour. This one is 3 hours. 1.5, 2, 1, 3, 5, 7. I don't know. I missed a few. 0, 1. It's also possible to have 0. It means simply you don't need any time to go from here to here. And probably if you have 0, there is a chance that you can put them together, but not always. We will see, because I need a few strict rules. And it means in this picture, this activity on these activities, so these two edges have to be finished before the vertex star can be reached or can be considered. So this is quite clear. You need to finish an activity before you reach a certain edge, a certain vertex.
Actually, one protected, like completed.
It is. Let's wait for a second. In the algorithm, it is. So how to build? I'm not sure it's correct. No, it's correct. But there are a few rules for building such a network or such an oriented graph. So rules. This is why we implement these rules, in order to be precise and in order to run some algorithm. That's it. Rules for constructing a network. And they are quite natural rules. First, it should be a acyclic digraph, which means oriented graph. You don't want any cycle because it's meaningless. There is a unique start, which is a start here. You start any activity, and there is a final unique point which corresponds to the completion of your work. So unique start, which means the in degree, dig in of what I called 1 is 0. You start here, and unique end or unique completion, which means the out degree of n is also 0. So there are two specific or two very special vertices. And this is important. The graph is simple. What does it mean? It means I cannot accept that two activities are taking place at the same time from A to B. But of course, this happens quite often. You have to do one thing and another thing at the same time. So how you deal with this situation? Instead of doing this, you start at A, you construct this situation, and you put a 0 here and a 0 here. And now this is, let's say, activity X, activity, no, I changed to my notation. This is not good. So let's say you have to go from 1 to 2, and this is A and B, the activity A, the activity B. Then what I do, I put A here, B here, with current time, 2 hours, 3 hours, and I add 0 times 0 time. So if I do this small trick, I put dummy vertices, then I end up with a simple graph. And the result is the same because there is no time for this one, there is no time for this one. The good point if this graph is simple, while the first one was not simple. Okay, so you have to use this small trick in order to respect this simple graph. You don't want to, and of course, loops are not accepted. You don't do an activity and arrive exactly at the same point. I hope not. Sorry? Yeah, Vic is doing this, but not everybody. Okay. Why do you want to have only 2 nodes? Of course, you can have from A to B. Yes, this is the simplest activity. Nothing else? What is the point? No, please don't ask or don't say too much stupid things, please. Okay. Notations. Now, because it's, you know, this is a general, when it's simple, there is one advantage. One edge is completely described by its 2 endpoints. So if you label the vertices, then you also label the edges, which is not true in this case. And remember at the very beginning, I took care of this. But if I consider only simple graphs, I don't have to give a name to edges. I can just call it, if this is I, this is J, this edge is the edge IJ, and everybody knows what I'm talking about. So notation, omega of IJ, so IJ are vertices. Omega of IJ is weight on edge from I to J. It's ordered, so I go from I to J. Then I define ET of I, which is earliest time for event at I. Indeed, for this vertex, you have to go through this and this, and through this and this before you can start the activity, or you can reach this point. So it's the earliest time for the event at I, and LT, these are just definitions. LT is latest time. Latest, it's slightly more complicated. Latest time for event at I, such that, so there is one more condition, such that, or without delaying the project. So it's slightly more complicated because check, I'm considering this vertex I. I want to know the latest time to arrive here such that I do not delay the full project, which means this latest time is related to this point because, you know, we have other job to do. So if the other jobs take longer, I can maybe wait a little bit here because somebody has to do this entire pass. But what is the latest time here so that it doesn't delay the full project? So that this event is not the latest one before we reach this. So it's not easy. You want to know the latest time so that you can start the activity from here to here so that there is no delay. Yeah, it's related to the earliest time here, indeed. I will come back to this. So I just give the definition for now. There are two more definitions. What is pred of J? Oh, maybe it should be press. I don't know. In the notes, did I put press or pred? Okay, if somebody can tell me if it is a D or a C. What is it? It is a set of I such that there exists IJ or edge IG. So what is it? What all the one which are before J,
Like
one step before. So there exists one edge between I and J. And what is the success or this? Yeah. Or I should. This is the set of J such that there exists an edge from I to J. Be careful, I change on purpose. Here I define for I, here I define it for J, but the definition is symmetric. Okay, and we have just one more convention. This is clear. What is the earliest time for the first edge? It's 0. You start your work at 0. And what is ET of J? You observe that this is a max of, this is not a convention, sorry. This up to here, it's a convention, then it's observation, I should mention, observation. How do you get ET of J? Earliest time for J, it's a maximum over all I, which is in the press or pred of J. So the one on the, just on the left of J of ET of I plus omega of IJ. No maximum. Think about this. I give you 30 seconds. Think about this. Why is it the maximum? Look, take this point here. You can start, or you reach this point by 2 paths. So you have to reach first these two and take then a certain time for these two activities. So the earliest you can start this event is the maximum here plus this length. So it's indeed the maximum. Okay. Yes. Now, algorithm. How much time? No, you won't have time to present the algorithm, but there is what is called the earliest time algorithm. If you haven't written any report, I encourage you to look at this, maybe do an example. So what you input this AOA network. And what is the output? You get ET of 1, ET of ET2 up to ET of N. And there is not a difficult algorithm. You just need to do it recursively, which tells you, you give this input, what is the earliest time when you reach this point, and this point, this point, this point, and this point, and this point. And yeah, if you understand what is going on, it's not difficult to, it's based on this idea. And yeah, you know this one, then you easily compute these 3, then you compute the next one and so on. So I let you think about it, how to do it. Now, so it gives you this algorithm, gives you the earliest time for all vertices. Now you want to compute the latest time for all of them. So I need to replace this formula by something similar, but for the latest time, which you need a few more minutes just to understand what is going on. Earliest time is not difficult. Latest time, I give you a formula for latest time. So what we consider, we have consider, let's just do the picture. We have I, edge j. And I'm claiming that the latest time at I is the minimum over j belonging to the successors of I of LT of j minus okay, please think about the meaning, and you can just use the picture. You want to know the latest time at I. Remember, it's the latest time so that you don't delay the full project. And so it means if this is I, it's related to the next one. So the latest time for I is you go to the next one. Oh, sorry. Yeah, this is I, this is j. So you go to the next one. You look at its latest time and you go backward because you need exactly this time to do this activity. And here it's easy. So maybe I should, okay, let's take this. This one is I because here we have only one after. So no. Take I here. What is the latest time for this one? You need to look at the two successor, these two guys, and you have to look at the latest time for this one minus this duration, which is quite easy in this case, and the latest time of this one minus the time you need for this activity. And think about it, the minimum is going to give you the latest time for this. It's not completely trivial, but just make a few examples and you will see that this is indeed the formula that you need. And then there is this latest time algorithm, which again, the input is AOA network. And the output is LT1, LT2, up to LTN. And it's not a difficult algorithm again, but instead of using the formula there, you need to use this one. And just the difference is, in fact, you start here and you go backward. While for the first algorithm, you go forward. For the second one, you go backward. Probably you give a certain name to this one if necessary, but I don't think you need it. No, you cannot assume that, okay, the latest time for the last activity, is it 0?
No. Just for the inside the program, and we put everything minus, and then we shift everything.
Okay. This is your job to find a way to implement this. No, I said no. I want to finish just, so these two algorithms are not difficult. They are presented in the notes. You just need to think about it. But why is it useful? What do you do with this? So what is interest? So you compute the earliest time and you compute the latest time. And there is one more notion is, suppose you are here now, how long you can wait until you start this activity? Because if you are lazy or for some reason you want not to start immediately this the activity here, maybe you can wait a bit here without delaying the full project, because let's say the guy here need more time. If you're already here and this guy need more time, then you can just rest for a while before you do this. And there is one notion related to this, and this is the last one, which can be computed with these two algorithms. So I set TF of I for it's called total float at a total float. Oh, sorry, it's for edge. Total float for IJ. Yeah, because, okay, this one was not a good example, but let's say you are here, how long you can wait until you start this activity, or how long you can wait until you start this one. And of course, it might not be the same. So the total float is for an edge, the total float for the edge IJ for edge IJ. I give the definition is the amount of time or the length of time, amount of time the start of activity on IJ, the amount of time the start of the activity on IJ can be delayed. How long you can wait until you have to start without delaying the full project. This is the idea. So the total float is this amount of time the start of the activity on IJ can be delayed without delaying the full project. Of course, you are not allowed to delay the full project, but still, if you can rest for a while, you are going to do it. And this is the final lemma for today. There is a way to compute this with the ingredients I mentioned before. It would be nice if somebody proved this. I don't think I put it in the notes. This total float for the edge IJ is equal to latest time for J minus earliest time for I minus omega of IJ, which is not completely surprising. Latest time at J ET minus earliest time at I minus, of course, the time you need for the activity on edge IJ. So if you think about it, this is not surprising. Now, the first algorithm gives you this activity. Oh, sorry. The first algorithm gives you this number. The second algorithm gives you this. So you have a way to compute everything. Of course, you probably do not need this for a simple task. But suppose you have to build a university. You have to build many, many things simultaneously. It's probably interesting to do this. Or I'm always surprised when they built a new airport. It seems to be so complicated, and still people are able to manage building such a big thing. Probably they're using such a nice graph or something more advanced. But I mean, these kind of things are useful. Okay, yes, exactly on time. There is one more notion, I'm not going to write it. There are critical paths. What could be a critical path in this? It's a path where you really have no time for, there is at each edge, you cannot wait. So critical path is in a sense, the longest path. Because if you delay at any place in a critical path, then the full project is delayed. And of course, there should exist such a critical. Okay, I suppose, I'm not sure. I suppose there exists always a critical path, but if the graph is more complicated, maybe not. No, not unique. Yeah, it may exist more than one, but I'm not even sure that exists one. Think about it. Is there always a critical path or a path where the total float is 0? Probably yes. Okay, if somebody wants to check question, and the definition is in the note, is there always a critical path? Okay, that's all for today. Thank you. Next week, we work on a different topic. If you have any question online, you can ask me. If you are not here, I encourage you to watch the recorded version. There is a recorded version of all these lectures, and I encourage you to do reports.